Hi everyone, very good morning. I usually plan to share my session with Professor Schahram, but today he is not here. I continue both sessions on behalf of Professor Dustdar. So the talk is on distributed intelligence in computing continuum using active inference. So this talk covers I start with a brief introduction about distributed systems and state of art and how the distributed systems evolved since 1960s, what are the different distributed system models, and currently how the compute continuum emerging, followed by what is the need of intelligence in distributed systems. And we primarily bring, instead of regular artificial intelligence and machine learning algorithms, we try to bring human intelligence, like how our human body works, into compute continuum systems. So I will explain how human body is more similar with compute continuum systems, followed by how to apply human intelligence mechanisms in distributed compute continuum systems to solve various problems. Here I pick only 3 problems. One is how to monitor the devices and their health condition, and how to cure in case if any problem occurs or any specific device or some unusual events occur within the distributed computing continuum network. And then I introduce the protocols, data protocols, which is a very old topic. Most of the protocols use very static rules and regulations. We try to implement some intelligence techniques within the data protocols, and what are the different ways or possibilities and what kind of problems we can resolve by incorporating intelligent mechanisms in data protocols to make it more intelligent and help to give a better experience and quality in compute continuum systems. So finally, coming with the active inference. So what is the role of active inference to make compute continuum systems more intelligent, and how efficiently we can handle the resources to gain a better quality of experience and service in compute continuum systems. So these are the major topics which we cover for 2 sessions. We start with how the distributed systems evolved. Around in 1960s, the mainframe computers was the first distributed systems, which is a centralized system, I can say. So the computers usually send the data to mainframe computers, there the computing happens, and then the response go back to the request from where the computing device requested. And it further evolved, like around in 1980s, 90s, the intranet initially, like intranet and local area networks are evolved. So after this internet, after the internet gets started, the distributed systems start evolving very quick. Then it starts initially like cluster computing, where a set of devices or computing entities work together to provide a service or complete a task. And later, a grid computing is introduced to overcome the centralized failures, for instance, a single point of failure or connection failures in the cluster computing. They go with a grid computing, where a single node is act as a leader, which distribute the work among all the computing entities in the system. So here also a similar problem occurs similar to a single point entity. When the grid compute means when the grid fails, the whole network is not possible to access. And then cloud computing arrived. The cloud computing, it's a centralized system again. So in cloud computing, all services work at one single place, and services are provided by one single entity as a central vendor. But cloud computing increases the latency and also vendor locking system. Then it further evolved both serverless computing and fog computing together. Fog and edge computing together bring the resources pretty close to the user. Serverless computing, its backend is a cloud, but that means the user no need to worry about the vendor locking system or background computing sources. Just manage, follow the functions and code which services you need, and automatically enable and useful. And then The next and current state of art is distributed computer control systems, where all the computing entities work together to finish a particular task. For instance, here, various devices including edge devices or data sources, something like IoT or sensing networks, can gather a vast amount of data, and this possibly try to execute within an edge. As we know, the edge resources are very limited, not always possible to complete all of our tasks within edge. So when it is not possible to complete the tasks at the edge node, just forward this computing task to a higher level, which might be fog or cloud, sometimes even high performance computing machine. So the infrastructure of computing kernel systems includes from small computing devices to high-end high-performing quantum computing machines. So these all computing machines together work to complete a particular task. Whether it is the small task, let's try to finish at the edge nodes. If it is a high-end task and require more computational or data space, they move forward to the higher layers, such as fog or cloud, even high-performance computing machines. Here, the main problem occurs is the heterogeneity between the device when accessing the services or performing the computations in between, like when we send one device to another device. So the vendors of the devices are different, and models and softwares are different. So interoperability plays here a major role and challenging issue to address in distributed computing machines. So distributed computer control systems can be incorporated in various use cases or applications. For instance, smart cities, where a variety of applications use smart technologies. For instance, smart hospitals, smart buildings, traffic, etc. There are like 30 different entities needed computing resources from a small scale to large scale. So here we can bring the distributed computer control systems to provide an efficient services. Also in our healthcare, wearable devices, for instance. So currently, many people are adopting the wearable devices. Almost majority of the people are started wearing smart devices to monitor their health condition. And recently, there are several wearable sensors are evolved, and now the people are using different wearable sensors to get the data or insights from our own body and health condition. So the sensors useful for collecting the data, like based on various signals or various signals occurring in our body. For instance, how much we walk, and wearing the smart shoe to measure like quality of our walking, and wearing the specs to see virtual reality kind of things. So the overall wearable sensors is currently growing in a higher speed. So these devices need, like, different devices are collecting the data, and each data is different, like interoperable, not a similar data. Such kind of different quantity and quality of data need to be analyzed. So such cases also needed distributed computer control systems. Further, I can also say industrial applications to make it speed, to make it the industry production growth rate or higher speed. We also can use in industry. We can bring these distributed computer control systems. Overall, the advantages and limitations with the distributed computer control systems is we can optimize the bandwidth, because we try to compute most of our computations within at edge. So we don't need to interact with the higher entities if not required. Instead of in cloud, we every time need to go far to the cloud. So, instead, we can optimize the bandwidth and try to compute as small tasks within the edge devices. No need to send to cloud every time, and then bring the cloud when edge devices fail to perform any particular task and it feels higher load, then we simply move. So in this way, we can optimize the bandwidth, and also we can we can improve the scalability and availability. So if any particular edge device fails, we have alternative computing devices like cloud computing, which can perform the computation, which increase the availability, and also whenever we need higher computing resources, which is easily scalable between the compute continuum layers. So it's easy to scale and also increase the availability, and it reduces the latency. Of course, we are using most of our computations at edge layers, so it's easy that this will reduce the latency, and also optimize the resources. So how we can optimize the resources? We can apply distributed computing even within the edge, between the edge devices to avoid to go until the cloud. So this distributed edge environment also can optimize the resources or cost of paying to the cloud devices. So in this way we can manage the resource, means we can optimize the resources. And load balance, as usually I said, we can distribute among the devices. So it's easy to distribute and reduce the load on a particular device or particular computing entity, so that it's easy to balance the load. And then reliability and flexibility. So it's very reliable, of course, and flexible to moving our computing task among edge to cloud or cloud edge, or even when required goes to high performance computing unit. But when we come to the drawbacks or limitations, we can say interoperability is a big issue, because we are using multiple devices of different types of devices in terms of size, capacity, computing, processing or GPU sizes, even the vendors, there means instructions, pipelines, even different between the devices. So this is one challenge which most of the researchers try to address, this interoperability issue. And data synchronization. So when we are moving the data from one place to another, one device to another device, or one layer to another device, it's necessary to properly apply the synchronization between the data or tasks when we are executing between different layers of compute continuum. And governing the resources is also another challenging, because we have plenty of devices. We need to maintain, means we need to keep it available whenever it is needed, and maintaining these devices is a complex and hectic task. And privacy, since we are moving the data from one layer to another layer, between one device to another device, privacy is also privacy itself another challenge. Then we move to distributed intelligence in compute continuum. As we see in compute continuum, the tasks are distributed and working. So why we need intelligence in distributed compute continuum? We are working with multiple layers and multiple devices and more diverse devices. So it's difficult that every time we need to manually adjust which computing device or which layer we need to perform the computations. Thus, we need to choose or we need to implement intelligent mechanisms within compute continuum systems, so that they can automatically autonomously decide where or which device the computation need to be performed, or which layer the computations need to be, and how busy the edge nodes are. So if the edge nodes are busy, how can, even though the task is able to complete within the edge, how long I need to wait to push my task to the edge layer, or simply I can go to the cloud and finish before my waiting time. So there are plenty of things we can think to apply intelligent mechanisms in distributed compute continuum systems. As we see, most of the techniques in the literature, and whenever the intelligence comes in the mind, people start thinking about artificial intelligence or machine learning technique, or even some statistical mechanisms. So bringing artificial intelligence or machine learning techniques in compute continuum systems might be a challenging task as we feel. Yeah, they are good algorithms and intelligent algorithms. They bring the intelligence to the distributed systems, but they also bring several challenges when we work with the distributed compute continuum systems. For instance, if I need an accurate learning model, I need a precise data set and also a huge input to make it my model more accurate. But we are working with low computing devices like edge or IoT. Putting such a high load on IoT or edge devices is a bit tricky task. So we can't put or store such a huge data or huge label or huge data or training data to train the models is a bit difficult task. So in this case, all the time we need to depend on the cloud or high performance computing machines. So that our goal of using all the computing sources might fail. And hungry with the computations. So most of the machine learning or AI algorithms need high computing capacity to perform the training and learning models. Since, as I said, connected with my previous point, since we want to use the entire compute continuum and putting all our computing sources at one particular place like cloud or data centers might be, we miss the goal of compute continuum. And also relatively expensive here in the sense, so we need to spend more time on training, we need to spend more time, more cost for the computing resources to gain the learning models. And there is a possibility for advisor attacks, which means there is a chance for our computing machine might misunderstand when learning about the distributed computer continuum systems. For example, as we see plenty of devices, each device configuration is different. For instance, I want to run my configuration, all devices, my whole computer continuum devices configuration data to learn. Each data file is different. It might be chance that these machine learning algorithms misunderstand or misinterpret when learning the model, and might be chance that it might generate some wrong models. And another challenging with artificial intelligence and machine learning algorithms in general, like estimating the accuracy level while streaming or while running the computing machines is a bit hard. And also the overall resource constraints. So what we understand from this is, let's move from artificial intelligence and machine learning algorithms more accurate, which can perform with limited data as possible. We try to bring a human intelligence or human body working mechanism into compute continuum machines. So what we understand from human computing machine and how our whole computing continuum environment is pretty similar with human body and how complex systems these two are. So we know our human body contains a skeleton composed with the bones and nervous systems. So our human body contains the nervous systems and cardiovascular system. These three systems are like physical parts of our body. We can treat as an infrastructure which is similar to our compute continuum, distributed compute continuum. And we have also lympathetic system and endocrine systems within our human body. We can treat them as a regulation systems which gives the protection to human body from various parts. So we can go a little deeper into nervous systems. We know our body spread with several neurons from human brain and connect with various other parts of body, maybe through spinal cord. So these neurons spread across and give the signals to human brain, and human brain perform the computations like a huge computing machine. It performs almost like 86 billion neurons. The human brain is capable of computing such a complex things within our brain. Then cardiovascular system. This is a bit tricky. Cardiovascular system usually help for spreading oxygen across the body and generating white blood cells and hormones, controlling the hormones and supply the nutrients to other parts of our human body. And recent study found that as we think in general, in human body there is only brain which is capable of thinking or processing and making decisions. But in 2019 there is a study found that in heart we have around 40k neurons. We know what neurons can do. So how we have the neurons in the brain, similarly we also have the neurons in heart, which means that we know the neurons capable of learning and decision making, which means not only the brain, other parts of human body also have the capability to perform at least not similar to human brain, but at least there are some computation or decision making capacity happening. So similarly, not only in a heart, the studies also found that a limited number of neurons available also even in our gut and various other parts of the body, which means based on this analogy, I can say human brain is not the only entity, like not a centralized machine to perform the computations in human body. So the neurons spread across the body in different organs, which means that our human body is a complete distributed environment. We can go more deep. Then lymphatic system, which is specially protecting, means which acts as immune system, immune system, and try to avoid if any outside or foreign entities enter in our body. We try to fight and protect within our body. So this can be sorry, and then we can go pretty close with this analogy. We can see the devices and sensors in our computing continuum machine. We can consider them as a skeleton of the distributed compute continuum, similar to human body. And the communications and data flows we can consider as the nervous systems or cardiovascular systems, which are mostly communicating with various parts of our body, means with the skeleton and other parts of body. And also our neuron system will help to learning and knowledge, and we are performing these learning operations in cloud or edge, depends on how they are capable to compute. And these computations we can consider as the learning happening in distributed compute continuum systems. And also the regulation systems. The regulation systems such as elasticity and self-adaptable systems. So like as I said, this lymphatic system and endocrine system, these are helpful for protecting our body, and also they helpful for self-adaptable. For instance, I move from one hot place to cold place. So our body very quickly understands from the sensory data, like how it's from outside environment, how it is sensing. So very quickly it tries to adapt and change our body conditions to adapt a particular situation. Of course, it's a more medical and tricky topic. I don't want to go more deeper, but it's try to adapt according to the condition and according to the environment when you shift from one environment to another environment. Let's take a simple example. We sit in an air-conditioned room, suddenly went outside with exposed to sunlight, your body starts sweating to make your body cool down. So similarly, so this kind of self-adaptable possible in human body to bring it into machines. and also fault tolerant systems. I can explain fault tolerance how we can do when we discuss about monitoring the devices, and privacy security. And from the human analogy, what conclusion I came, what are the different things the human body and human ecosystem is capable to do is our human body continuously acquire the feedback and try to adaptable. As the same example which I mentioned, you sit in an air-conditioned room, when you go outside, it simply collects the outside weather, your brain collects the outside weather, and then it starts thinking, yeah, it's hot place, your body need to get a normal temperature, so it starts getting sweating. So it keep on acquire the feedback from the environment and try to make it adaptable. And it's also very tricky to how the communication and coordination happen between each and every organ in our body. So it's a very big topic to discuss. In our body cells, they communicate very efficient way, and they know to whom they need to communicate when required. So it's a very tricky, but our human body know. It can open the communication when it need to communicate with a particular other organ to send some information, and in the same way the other organ know from where I need to get or receive the data. So the human body is very efficient in communicating with one body organ with other body organ by using these neurons. And decision making. I hope I don't need to talk more about decision making mechanism made by human body. So we know how efficient the human is making his own decisions in a particular situation. So the decision making mechanism of human body is very efficient compared with any computing machine, and it also connects with consciousness, how conscious when you make decision, and we know the future effect or future things what will happen based on our current decision. We are pretty aware of these things when we make the decision. And our human body have the capacity of self-healing. For instance, nowadays in India we know very well how this self-healing mechanism works because we not directly go and take medicine for small diseases or small things. So most of the people directly go and take the medicine if any disease or anything happen. But usually our human body have the capability to heal if any problem occurs. For instance, if some knife cut happen, it know how to heal it and make it normal. If you got fever, it know how to heal it and get normal. It might take 1 or 2 days, but our human body know how to heal your body by itself. So these are the major features of human ecosystems which we can replicate in distributed continuum systems to make it more intelligent. For instance, where can we implement these human ecosystem features in distributed compute continuum systems? For example, we have idea about predictive maintenance. The predictive maintenance can find the problems based on previously occurred problems. If any new problem occurs, it don't know how to rectify. So, but your human body know when you change one location to another location, or if any new virus enter in your body, it know how to protect your body from this virus. So what I am trying to say here is that if we implement human ecosystem or human intelligence in distributed compute continuum systems, or maybe in other fields, we can find good solutions which can be solved before some problem occur, or at least we are aware that what kind of problems can occur in the future, what kind of solutions we can impose to resolve such kind of issues. And the communication, as we discussed, like synchronization, data synchronization is one of the issue with distributed continuum systems. We can replicate how the human organs are communicating the similar, like both sensory data or actual data. We might bring such techniques in distributed compute continuum systems to make it communication more efficient and precise, also privacy preserving. Since we are communicating one-to-one entity, we can also preserve the privacy. And decision making, bringing decision making and consciousness in computing machine is little bit difficult because consciousness definitions are still not clear, and still there is a lot of work going on consciousness and how to bring consciousness in computing machines. Maybe later, after some years or some days, we might bring consciousness similar to the human body into the computing machines to make it more efficient and make it like work by themselves. And self-healing mechanism, we might find if any fault occur within the system. So without a human try to resolve the problem, let's system solve by itself. Let's try to heal by itself. So the self-healing mechanisms also can bring to avoid human interventions into the computing machines, so that we can reduce the downtime, like no need to wait until a person go and solve if any particular problem occurs. So in this way we can, the self-healing mechanism can be reimposed in compute continuum machines. The overall, to be like a package, we can impose several human body features, how human body is able to survive by survive with various factors. We can bring this directly in a compute continuum system to make it more intelligent and adaptable to the environment, work by itself without getting more human interventions into the systems. Let's discuss our first problem, which I thought monitoring and diagnose or cure if any problem occur in distributed compute continuum system. This is just an analogy which we recently tried with some learning techniques, but there is a high possibilities one day we will achieve this. So this is a high level work. I try to describe what we try to implement in a system. So we try to bring data from compute continuum machines, like we have data in various forms, especially devices data. So we bring these devices data into, like for instance, system configuration file, network configuration files. So the data is diverse, and we bring this data, we take this data and start analyzing more frequently to understand what's happening within the computing machines. So here we pick representation learning algorithms to understand the patterns of the data to identify unusual activities. So we feel representation learning algorithms might take the less computational efforts, so we pick the representation learning algorithms, especially based on learning, based on structured learning techniques. So we extract the knowledge from this, and based on this knowledge, we can understand is there any fault within the system, is there any fault during this monitoring or knowledge extraction. It might simply take the decision what to do next. Otherwise, it can also notify to the administrator, depends on what kind of issue it is. If it is, for instance, resolvable, for example, a configuration, a particular software configuration is failure, so we might add some instructions within our code to reconfigure the software or reboot the system. For instance, if the network connection failed, it might be difficult to work with the code. So we must notify to someone to go and resolve the problem. So if it monitor, it directly, if it able to solve, it directly take the action. If it is not able to solve, the decision will still directly bring to an administrator, or we can also visualize what kind of problems occur within the system. This knowledge can also use to predict what kind of problems, possible problems can occur in the future. So this prediction also can help to take the predefined decision to not occur such a problems. For example, your network is getting slowed down. So what can you, what are the alternative steps we need to take to save the task or computational loads or etc. And coming to the actions are where we can implement this human intelligence, we bring into action. So here we find one of the traditional technique, how our human body is trying to resolve or trying to self-heal when some wound happen. For example, the knife cut or slice. So how the human body try to resolve this problem. I am not talking about medication. Human body itself with lymphatic or endocrine, it use all its knowledge and how it try to make to solve the problem. So usually human body, when some wound happen, it's solved in 4 stages. The first stage, hemostasis, which means first control the bleeding and stop the initial damage. So the initial step is first stop the bleeding, try to stop the bleeding, which means control the damage of the seriousness of our body. And then it creates the inflammation, which means it try to clean around, it try to clean around the wound, it try to clean around the wound to repair the new issues. And in the third stage of proliferation, which means our white blood cells from various parts of our body, they try to move towards to the wound, like it brings like whatever the white blood cells need, they try to bring towards to the wound to make it avoid from the damage. So this is the third stage. And after the white blood cells come, they start repairing the tissues, and after repairing the tissues, it's almost resolved, but your skin not look like previous. Then what you do, you try to reshaping the skin, which look like as usual before wound happen. It might take a long process, but it involves different stages like this. So we can interrelate with automatic or self-healing mechanism through action agent who take the actions. We might implement similar things in distributed computer control. So first thing, when some damage happen or we notice our knowledge predicts or identify there is some device is in trouble. So the first thing we need to try to find, because of this particular damage, there is no other damages will happen. Maybe, for example, if internet is slowed down, which might happen of computing the task or transmitting the data between other devices. So how can we control? So the first step is try to, for instance, the device is getting, energy is getting down. So the first thing, avoid data routing with this device or try to retransmit using other devices. So the initial step is try to control the damage which not affect on the entire performance. And the next one, activating means try to find what solution we need to apply, which means that activate the particular program or instructions to try to activate the instructions, and then start the repair or try to resolve the problem. For instance, if software is failed, try to reconfigure and try to reinstall the new version of software. And if any data is lost, try to recover the data. So if any hardware failures, it's difficult to rectify the hardware failures through our programming instructions, which might be notified to the administrator, similar to when the problem is not able to solve, we go to the doctor. Similarly, we can send the problem to the doctor directly, and then replace, like reinstall or rebuild the system and make it ready to work as a normal. So we try to implement this technique by using various learning techniques and try to implement these models by using zero-touch provisioning, zero-touch service provisioning to bring these concepts in this and try to implement this technique. And data protocols and make them intelligent. We know there are several data protocols currently in the market, and some of the popular ones include Constraint Application Protocol, which is COAP. So how the Constraint Application Protocol works, it works between client and server and transmitting the data from client to server and send acknowledgement from server to client. So the data transmission happens between two entities. So how this data transmission happens usually? So they use a fixed time. There are several functions they use, like binary, web, and there are several functions used. So what these functions will do, they calculate when a particular packet fails. These functions calculate a new retransmission timeout when this failed or dropped packet will need to send again. So most of these functions calculate the retransmission timeout based on a previous round trip times and retransmission timeouts, and they keep on increase. For instance, if we use BUB function, they increase, like initially it takes 2 milliseconds to send the data. When it failed to send, then it increased to 4. So these 4 units of time, the packet is waiting in a queue. If it's unable to deliver this time, it again increases exponentially, which up to 8 milliseconds, then 60 milliseconds, 32. So it increases like binary into to the powers when it failed to transmit the data. So which means that same packet of data will reside a particular queue for a long time, which decreases the throughput as well as how long we keep a particular data packet in the memory. It unnecessarily holding or unnecessarily misusing our queue space. So here we can come up with a new learning techniques based on delivery, based on bandwidth. So we can find or we can apply learning techniques here to identify the accurate time. When means you decide an accurate time based on your historical data or the condition of receiver. You can decide a particular time with one shot the particular data packet will be delivered. So instead of you wait for a long time and increasing the exponentially from 2 to 32, you decide one number between this based on the learning and prediction how much time and your queue capacity. You can decide one time in one shot. It directly delivered to the data packet instead of it just go and try and fail, come back. So we avoid this kind of iteration and unnecessary resource utilizes when we identify a right function to decide the time. And popular MQTT. So the MQTT protocol, it's a public subscribe protocol. A publisher publishes the data and subscribers subscribe the data, and here the message broker acts as a mediator to control all these activities. But if we see more close to the MQTT message broker, it has many restrictions, especially message expiry. It's very static expiry, And priority, we have only 0 to 3 priorities. And also, priority, it's just 0 to 3, like we can assign one of these four categories. So here we can bring learning techniques or make this particular message broker intelligent to take the dynamic decisions instead of like if you arrange a particular sequence of priority when you send the data. For example, if all messages go a particular priority, which might be difficult to deliver due to overlapping with the queue. So we can find an intelligent techniques here. We can identify some intelligent mechanisms here to make this message broker more intelligent and adaptable according to the conditions, like both receivers and sender, which without losing the data, which transmit the data from one to another. Similar message, similar to MQTT, we have another public subscribe protocol is AMQP. So in this AMQP, instead of making a single queue in a message broker, it just split multiple queues to maintain separate topics. So the client can choose any one of the topic or multiple topics and to receive the data. So here also, so this how to decide the number of topics. It's static. We need to predetermine or predefine how many topics we need to decide our queue sizes. So here we can bring the intelligent mechanism to dynamically use the memory by splitting the number of topics and also each individual, like here, if you see here, each and every topic takes equal memory size, but all the cases which might be not necessary. For instance, some people heavily use Facebook, some people heavily, very minimally use LinkedIn, for instance. So you allocate the memory size for the queues, the number of packets in a queue may vary, depends on the subscribers requirement and how frequently the publishers are publishing a particular topic, which is also similar in DDS, data distribution services. So here also we can find dynamic mechanisms for to identify the number of topics based on the content type. So we try to make this topic selection dynamically. Maybe we can also bring natural language processing to find more frequent content or sentiment analysis to define topics to transmit and maintain this data bus very efficiently. So to the conclusion with all these protocols, so more currently whatever the data protocols or application layer protocols which we are using for data transmissions within a IoT or internet, these are static and fixed rules. They follow whatever the rules we decide. Okay, do this, do that, do this, do that. It's like a rule-based static rules each and every protocol follows. We have both advantages and limitations with these static definitions. First thing is low overhead, because you know what you need and you define exactly what is your requirement. So you don't need to add any additional instructions within your protocol, and it not take like a huge memory or computing resources to perform. It just execute instruction by instructions when running the protocol. And also if any fault or misconsumption happen within the protocol, you can easily track because you know how each step is processing. And predictability means failure predictability here. So if any failure occur in the protocol, it's easy to backtracking to identify where exact problem occurred. But in other side, when it comes to the limitations, sorry. Yeah, when you come to the benefits, if you bring this, it might be scalable, it might be adaptable, like scalable in a sense, for instance, we can adjust the memory, queue memory, however we want, according to the requirements and conditions, and which might make the adaptable according to the requirements of the subscribers or publisher, which means it start moving by itself. I'm sorry, it's okay. So when we implement these intelligence mechanisms, summarizing in overall protocols, we can efficiently and dynamically filter the messages to send to whom exactly we need to send, and define the message expiry. So in general, the message expiry is fixed for each message. Sometimes based on a priority, the message expiry is fixed. So we can identify the message expiry dynamically, and this congestion control especially happen in COAP protocol because of multiple retransmissions leads blockage of bandwidth or memory, which might be happen buffer overflow or overusing the bandwidth, which might lead to lost many data packets, or it make the congestion in the network or memory. So these kind of problems also solve when you apply intelligence mechanisms in compute control systems or IoT devices when you develop data protocols. When you come to the implications, if you want to implement learning techniques within protocol, which need additional resources to perform the computations, and where this learning happen. It should happen in message broker, or in publisher, or in subscriber, or in edge device, or cloud device. So deciding the exact location where we need to perform these computations in protocol is also challenging because of the limitations in memory and computations. And also, as usual with AI techniques, identifying the runtime accuracy is also difficult. Finding appropriate algorithm which resolve multiple problems, multiple issues, which we mentioned, like filtering, deciding the dynamic message expiry, blah blah blah. So this all. So we need to identify a particular learning technique which can resolve multiple problems, which is also difficult. So these are techniques we can bring intelligent mechanisms in active inference to make it dynamic and intelligent protocols. The goal is that the goal of making new protocols here is that make it more intelligent, adaptable, and now the paradigm is changing. Multiple devices are emerging into compute control systems, which includes the interoperability and from low to high devices. So by keeping all these constraints in the mind, we need new intelligent protocols for compute control systems, even in the internet. So dynamic and intelligent protocols required in our current scenarios and coming days. So still we develop one intelligent protocol to avoid the congestion control, but still we are looking a possibility and even bringing generative AI or more intelligent techniques and try to implement this human intelligence which we talked in our previous slides. We try to bring to develop new protocols in compute control systems. So before moving to the next topic, can we take a break?